In this video, we will look at calculating the temperature at which a reaction flips from being spontaneous to non-spontaneous or vice versa, using this reaction with NO and O2 coming together to form 2NO2. And when you're asked to calculate the temperature dependence of spontaneity, we're always going to be working with this kind of equation. Delta G equals delta H minus T delta S. And the answer to this problem is solving for T when delta G is equal to 0. But in order to do that, we first have to calculate delta H and delta S for the reaction. Okay, so let's look at doing that first. Delta S for the reaction is going to be equal to the sum of delta S naught for the products minus the sum of delta S naught for the reactants, keeping in mind that these guys have to be multiplied by their stoichiometric coefficients, which I've shown there as n. So my one product here, 2NO2, right, I'm looking at my product, so a coefficient of 2 times I look at the entropy value for NO2, 240.1 joule per mole Kelvin. That takes care of my products minus my two reactants. So NO has a coefficient of 2. Its entropy value from the slide is 210.8 joule per mole Kelvin. And I'll keep in mind all the reactants are getting added together. So here, one oxygen, and its value is 205.2. Okay, again, joule per mole Kelvin. So 2 times 240.1, right, is giving you 480.2 joule per Kelvin. The mole drops out when it gets multiplied by its coefficient. Over here I have a 2 times 210.8 plus the 1 times 205.2. That gives me a value for my reactants of 626.8 joule per Kelvin. Okay, so 480.2 minus 626.8. My delta S of the reaction is equal to negative 146.6 joule per Kelvin. Okay. I'm going to be wanting to work in kilojoules later on, so I'm going to go ahead and convert that right now because I know my enthalpy information and my Gibbs information is typically in kilojoules. So dividing that by 1,000, right, equal to negative 0.1466 kilojoules per Kelvin. Right, keeping my conversion over here was just 1,000 joules, 1 kilojoule. So that's the delta S for my reaction. How about the delta H? Same process. Delta H for the reaction. Okay, my products, just my NO2. Now 2 moles times the delta H value for NO2, which is 33.2 kilojoules per mole. That takes care of my products. Same thing for my reactants. Okay, 2 times NO, right, 91.3 kilojoules per mole, plus 1 oxygen, but I'm not given an enthalpy value for oxygen, which is not a mistake. Remember, the heat of formation of anything in its most standard state, and here we have that, oxygen diatomic gas, is just 0. So that drops out, and that's an old theme from chapter 5. So that makes this calculation a little bit simpler, right? 2 times 33.2, 66.4 kilojoules, minus 2 times 91.3, which is 182.6 kilojoules. So the delta H of my reaction is equal to 66.4 minus 182.6, negative 116.2 kilojoules. It tells me it's an exothermic reaction. It's an exothermic reaction with a decrease in entropy. So this is one of the situations where temperature flips, because if it was exothermic with an increase in entropy, it would always be spontaneous with no exceptions. But that's not what we have here. Now I have the information I need to go back to my equation. Delta G is equal to delta H minus T delta S. Okay, I said To solve for that temperature at which it flips, we're setting delta G equal to 0, equal delta H of my reaction, negative 116.2 kilojoules, minus T, what we're solving for, multiplied by delta S, negative 0.1466 kilojoule per Kelvin. Okay. So now I've got all the information I need to solve for T. Yep. Set this to 0 over here, so I'm going to bring that value over. Okay, 116.2 kilojoules is equal to, now I have a negative T multiplied by a negative value over here, so that becomes a positive, right? T times 0.1466 kilojoules per Kelvin. I'm going to divide both sides by 0.1466. 116.2 divided by 0.1466, and I got a final answer of 792.6 Kelvin, equal to my temperature, where that reaction flips from spontaneous to non-spontaneous.